Hey, welcome back. In this video, we're just going through how to solve a 3D statics problem. In this case, we have a 100 Newton rod. On one end, it's supported by a ball and socket connection, and on the other end, there's two cables that are connecting it to some walls. So you'll notice that this cable here is parallel to the x-axis, and this cable here is parallel to the z-axis. What we want to do is we want to find the tension in each cable, and then we also want to find all of the reactions at the ball and socket connection. So let's get started with a free body diagram. So looking here at the cables first, because they're cables, we know that they have to be in tension. They can't provide any compressive reaction for us. So we know the direction of the forces that will be directed through those cables. Looking here, we also have the weight of the rod that we already knew from the problem. And then we also have three reaction forces. So you'll notice that these are just like force reactions. We have AX, AY, and AZ. That's because of the ball and socket joint, as we talked about in the previous videos. The ball and socket, because this is fixed to the ground, it prevents it from actually translating if you apply a force in any of these given directions. But it doesn't provide any couple reactions. You can rotate or just spin this rod around in any orientation, and this ball and socket joint won't be able to resist that. So we're not getting any couple moments here as part of the reaction. We're just getting these force reactions. So for our 6 equations of equilibrium, we can sum up the moments here to simplify it a little bit as just the sum of moments about some point has to be equal to 0, and that will take into consideration the 3 components of moments that this can possibly have. So when we go through and solve this, we'll just do the sum of forces in the x, y, and z direction. And then we'll have our sum of moments about A, where R is the position vector from A to the point where these forces is acting on this object. And these forces by component are like so. And I guess what I should have done is I probably should have labeled here on the original drawing. So we had point A. I was going to be calling this point B. Call this point C, and I would call this point D. Sorry about that. That's why I said force FBC goes F from B to C and then B to D. Just forgot to write that on there before. Alright, so anyways, moving on, then what we want to do is we'll just expand this out. So we'll have our position vector cross our force for each of these. And you'll notice here the first 2 position vectors are the same because their lines of action are just intersecting the same point there that we're measuring the position vector from A to that point. And here we're seeing that it's the position vector for the weight here is half because the weight happens at the mass center, and so that's halfway along this beam, and so all the measurements here are taken in half. What we could really do is, I guess we could really define this as a vector, and then we could say that this is 1/2 of that position vector that we've called R. And I guess if we really want to get fancy, we can put in all those little vector signs. Alright, let's keep going and actually perform the cross product now on each of these terms. Then cleaning up each of these terms we'll get, and then one last step of just combining all of these together we get, and this single equation for the sum of moments about A can be broken back out into its individual components for X, Y, and Z. So all I did here basically is I just grabbed this line and set it to 0 as the equation for the sum of moments about the x-axis, because this is the x component of this. Same, this line becomes the sum of moments about the y-axis, and this line, the third line, becomes the sum of moments about the z-axis. So just kind of to summarize what we have, what we found here now, I'll just bring this down so we don't lose it. But we have our 6 equations of equilibrium. We have all of our force equations here, and then we have all of our moment equations right here. So here we have 1, 2, 3, 4, 5, 6. Those are our 6 equations of equilibrium. And then what we can do is we can just simply use substitution to just start figuring out what all of our variables are. The easiest one that I'm seeing right now will be FBD. We can just use this equation, simply rearrange to bring the 50 over to the other side and divide that 50 by 0.6. We can do the same thing here for FBC, where we'll just bring this over to the other side, and then we'll have 20 divided by 0.6. And now all we do is we just need to substitute these values into the other 3 equations, and we'll figure out what our reactions are at A. So for sum of forces in the x direction, AX minus FBD equals 0. Well, FBD is 83, so bring that over. So AX is also equal to 83.3. These are both positive values, and what that means is they are going the direction that we assumed on our free body diagram. So in this case, we assumed that because of tension, that the force would be directed in the negative x direction, and the way that convention works is we assume that direction, and when we get a positive number, that means that this is indeed, the force is directed in that direction that's acting on the rod. So we see a positive number for AX. Well, basically, if this rope is trying to pull the rod this way, AX has to resist it by pulling it this way. So they're showing up as positive numbers, but what might be a good exercise for us to do is to draw on the directions. So in this case, it's going that way. For this guy FBC, it was going off in that negative Z direction. And yeah, so then now we can just fill in the rest of these guys. So AX was equal to, again, 83.33. It's just opposing, and it's going in that direction, and that is, I guess we can just say that's newtons. When we look at AY, oh, this should actually be 100. I don't know why it says that. Here, 1 second. This whole time this was 100 newtons. I don't know why I wrote 200 there. 1 second. That's a typo. Okay. So AY minus 100, obviously AY is going to equal 100 newtons, and that will be pointing straight up. Again, we assumed AY was going up, and that makes sense because it's resisting the downward weight. And then lastly, we have AZ, and AZ minus FBC equals 0, so AZ is going to equal FBC, and we had 33.3 newtons, and then the orientation of that is positive Z direction, so it's going that way. And that makes sense because we're having all of these reactions. Every time we're having something pull in one direction, we're having the reaction just oppose it in the equal and opposite direction. So there you go. This is the answer to the original problem asking what are the tensions in the cables. Well, the tensions are here. And what are the reactions at the ball and socket? Well, those are here. And again, because this is a ball and socket, there is no couple moments that are being caused by that. So these are all of the reactions and tensions that we can possibly solve for in this problem.